This seminar will describe the ascentis line of HPLC columns with emphasis on the RP separation mode. Ascentis columns are retentive high-performance phases that are designed specifically for separation of small molecules. Method development is made easy because all ascentis columns have comparable retention. Since column screening normally does not require mobile phase change, method development can be rapid and easily updated. A comparison of selected Sepelco columns is shown in the next slide. The first four columns are designed for use in reverse phase methods with small molecules. Ascentis RP amide and phenyl fall into a category called polar RP phases, which should be tried when C8 and C18 do not give the desired results. The polar RP phases are polymeric in nature to impart extra stability and inertness to the phase. All ascentis RP phases show comparable retention and stability with very low background for different types of detectors, including mass spec. Ascentis silica should be used only for normal phase or aqueous normal phase applications when RP methods fail. Discovery HSF5 can also be employed in the RP or NP modes as a unique phase that often solves difficult separation problems. This next slide shows the well-known resolution equation, along with a further explanation of how terms are calculated. In nearly all modes of HPLC, some form of selective retention by the stationary phase is required for column resolution. In order to know whether a compound is retained, one must know the column void volume, V sub m or V0, by measuring retention time for a non-retained solute at a given flow rate. Once a column void volume or void time at a given flow rate is known, it will not change. If a solute elutes at or very near the void, resolution caused by stationary phase interaction cannot occur. Most textbooks recommend that all peaks of interest be retained with a K of 1 or greater for reliable quantitation. A K of 2 to 3 is much safer if it can be achieved. A K of 1 means that solute spends equal amounts of time in each phase. A K of 2 means that solute spends twice as much time in the stationary phase where selectivity occurs. When two solutes spend different amounts of time in the stationary phase, they have a different K value and a selectivity greater than 1. A selectivity value of only 1.1 is usually enough for complete resolution of 1.5. Try plugging different values of K and N into the resolution equation for a K of 2 and a selectivity of 1.1 to demonstrate that good resolution can be obtained with a moderate number of plates that are readily achieved with modern HPLC columns. C18 columns have become the industry standard as suggested in this next slide. The hydrophobic interaction forces that are dispersive in nature are often sufficient to allow C8 and C18 columns to retain and separate many organic compounds. However, results may not be optimum in all cases. Trial and error has shown that selectivity, retention, and efficiency can all suffer with certain sample types. In these cases, which occur as much as 25 to 50% of the time, polar RP phases should be explored. The next slide suggests that modern C8 and C18 columns are becoming much alike due to evolution of silica particles and development of improved bonding chemistry. Changing from a C18 to a C8 or from one brand of C18 or C8 to another may not produce a different, better result. When resolution is not acceptable for any reason, an alternate stationary phase with more polarity than C18 or C8 may be the answer. This seminar will describe how polar stationary phases, such as ascentis phenyl and RP amide, can play a unique and important role in changing retention and selectivity for certain classes of compounds. Similarities and differences are easily shown in the next slide, where log K values for two columns are plotted under the same operating conditions. If there is a high degree of correlation, a straight line with low standard deviation, the two columns have very similar selectivity. If the test mix and sample of interest has the same or similar compounds, there would be little reason to evaluate both columns. If a very slight difference in selectivity is needed, evaluating both columns could still be successful. Modern C18s have become very similar in selectivity, even for basic compounds, because silica quality and bonding techniques have improved to the point that silanol effects are minimal. The main reasons for looking at two C18 columns would be for improving peak shapes and gaining slight changes in selectivity. Even if successful with one C18 over another for a difficult separation, lot evaluation should be conducted early in method development. Although C8 columns often show similar selectivity to C18 columns, shorter chains sometimes show different selectivity because they can solvate differently with the mobile phase and interact differently due to the size and shape of certain molecules. Also, C8 reagents are smaller than C18 reagents and have improved primary phase coverage requiring less end capping. C8 phases show excellent peak shape and very high phase stability. The next slide describes some types of chemical interaction that can occur between sample and stationary phase. Nonpolar solutes with alkyl character will usually be retained and separated best with alkyl phases. If a separation looks promising on C18, but still requires optimization, small changes in the mobile phase should be investigated. Changing to a C8 column should also be investigated. Polar solutes may be retained and separated better on a stationary phase that includes built-in polarity, such as an amide, phenyl, or pentafluorophenyl phase. Ionic solutes may require phases having ionic character for best results. It is important to appreciate that complex molecules can interact by more than one mechanism, making it difficult to predict results without injecting samples. In this introductory seminar, we will briefly describe some types of polar interactions that can occur with RP-amide and phenyl columns and show some examples of improved retention and selectivity over C18 columns. The next slide confirms that solutes which are very hydrophobic and contain mostly carbon, such as simple aromatic molecules, typically show more retention and selectivity on C18 and C8 columns. Note that aromatic character of the solute does not make the aromatic phase more retentive, so the rule of like attracts like does not apply in this case. It is more often differences in chemical structure that create molecular attraction, retention, and separation. The next slide shows that small molecules with a polar functional group, such as nitro, hydroxyl, amino, or many others, can show more retention and selectivity on phases having their own built-in polarity or polarizability. This is the case for some simple nitroaromatics. The extra retention for phenyl is believed to be due to formation of strong pi-pi complexes between solute and stationary phase. Nitroaromatics are pi acids, while the phenyl phase is pi basic, which can help explain the stronger attraction to that phase. Any solute having strong dipoles can also polarize and interact with aromatic systems. Note that C18, C8, and RP-amide are about equally retentive, which suggests that the interaction is coming from the alkyl chain and is mainly dispersive in nature. The ascentis column line has been carefully designed to produce excellent results for a very wide range of compounds. When a C18 or C8 column does not produce an optimum separation, a more polar RP phase, such as RP-amide or phenyl, should be investigated without changing the mobile phase. This greatly speeds up methods development and allows simple, convenient automation of the screening process. We prefer acetonitrile storage, especially for polar RP columns, because it is a less reactive environment towards silica than either water or water-methanol mixtures. We also recommend that methanol be explored as the organic component or as a co-solvent with acetonitrile when polar RP phases are investigated. Experimental conditions are shown in the next slide for a comparison of ascentis RP phases. Selectivity was compared by plotting log K values for a large set of different solutes having acidic, basic, and neutral properties under these operating conditions. Note that LC-MS was employed to facilitate identification of solutes by their mass spectrum. Ascentis phases are specifically designed to be stable and highly compatible with all popular LC detectors. In this next slide, correlation is very high at 97%, showing that ascentis C18 and C8 are very much alike in selectivity. Differences increase for the more polar compounds, as shown by increasing scatter, and they decrease for less polar compounds. In general, changing between C18 and C8 phases would not be expected to be productive when a large change in selectivity is needed. Changing between one brand of modern C18 or C8 and another would also normally not produce a major selectivity change. This next slide compares ascentis RP amide with C18 and shows lower correlation, greater orthogonality at 70%. Again, one should note that scatter increases as solutes become more polar and decreases as they become less polar. The embedded amide group is able to interact with solutes by a hydrogen bonding mechanism as well as by other dipole mechanisms. Amide also has the important ability to shield solutes from silanol interaction, which often results in shorter retention and sharper peaks for bases compared to C18 and other bonded phases. This next slide, which compares ascentis phenyl with C18, shows even lower correlation, greater orthogonality at 41% for this group of compounds. A similar pattern of increasing scatter with increasing solute polarity is observed. Phenyl rings are pi-basic and can interact strongly with other ring systems and dipoles. The ability to form pi complexes makes this phase a very important complement to the ascentis RP amide phase when alternate selectivity to C18 and C8 is needed. The structure of ascentis RP amide is shown in the next slide. It is made from an imidosilane reagent in a one-step bonding method similar to C18, C8, and other phases. Polymeric reagents are employed to achieve maximum stability and low bleed with all modern HPLC detectors. The high phase load also makes the phase comparable in retention to C18 and C8 for easy column comparison without the need to change mobile phase conditions. Ascentis polar RP phases are more retentive than C18 and C8 phases for many polar solutes. Amides are part of a group of HPLC phases that are often referred to as embedded polar group or EPG phases. They include amides, carbamates, ureas, sulfonamides, and ethers. The next slide summarizes ascentis RP amide behavior. Retention usually lies between C18 and C8 for nonpolar compounds. But RP amide can be more retentive and selective for polar solutes, especially those that are attracted to the amide group by their ability to hydrogen bond, especially acids. Ascentis RP amide can also shield or protect solutes from silanol interaction, which results in shorter retention and sharper peaks for basic compounds. So amide phases tend to retain acids more and bases less. However, exceptions can occur when functional groups are sterically protected from interaction. Ascentis RP amide is easily wetted and is highly stable even in pure aqueous mobile phases, which is an advantage over most pure C18 or C8 phases. Reduced silanol interaction of the RP amide phase can be seen for a simple drug mixture in the next slide. The acid, acetaminophen, shows good peak shape and comparable retention on both C18 and RP amide phases, while the base, pseudoephedrine, is less retained and more symmetrical on the RP amide phase. Extra retention and tailing of bases on C18 columns is usually attributed to interaction with silanols on the silica substrate. The mixed retention mechanism by the C18 column results in a different elution order for the two columns. This is a common result for EPG columns when samples include both acids and bases. Generally, acids are more retained and bases are less retained on RP amide compared to C18 and C8 columns. This slide illustrates enhanced retention of acidic phenols on the RP amide phase. As implied in an earlier slide, this extra retention and selectivity is likely due to strong hydrogen bonding between the amide carbonyl, which is a strong hydrogen bond acceptor, and the phenol group, which is a strong hydrogen bond donor. The data in the next slide clearly shows that the RP amide column is more retentive and selective for catechols and resorcinols under these conditions. The EPG phase that contains an ether group is only slightly different in retention and selectivity from a straight-chain C18 phase because ether does not have the ability of an amide group to hydrogen bond with the phenolic group. Although comparing an ether phase to a C18 phase may be useful if only slightly different selectivity is needed, the most dramatic results for acids, such as phenols and carboxylic acids, will be obtained with EPG phases that contain an amide group. The next slide shows a gradient separation of compounds that are found in teas and many other natural products and nutraceuticals. Due to the common appearance of phenolic chemical structures in plant extracts, the resolution of RP amide for such samples is often much better than it is for C18 or C8 columns. Note that ascentis RP amide is highly compatible with LCMS because of its unique bonding chemistry. This is a strong advantage over many other amide type phases which can show a high detector background signal. The next slide shows molecules with multiple functional groups. It is very hard to predict which group might dominate interaction with the stationary phase. The reversal evolution order in this comparison could be explained by the ability of fluoxetine as a secondary amine to form stronger hydrogen bonds with the amide phase. Extra retention could also be caused by the presence of the CF3 group, which can act as a dipole or a hydrogen bond acceptor. The structure of ascentis phenyl is shown in the next slide. Like RP amide, polymeric reagents are employed to achieve maximum stability and low bleed with all modern HPLC detectors. The high phase load also makes the phase comparable in retention to RP amide C18 and C8 for easy column comparison without the need to change mobile phase conditions. Ascentis polar RP phases are more retentive than C18 and C8 phases for many polar solutes. Phenyl rings can interact strongly with other ring systems and strong dipoles. The next slide summarizes ascentis phenyl behavior. Phenyl retention is usually lower than C18 and C8 for nonpolar compounds, but it can be more retentive and selective for polar solutes, especially those that are aromatic in nature or have strong dipoles. Like RP amide, ascentis phenyl is easily wetted and is highly stable even in pure aqueous mobile phases, which is an advantage over most pure C18 and C8 phases. Methanol can be an important solvent for method development. There is reason to believe that acetonitrile may be able to dampen the selectivity of the aromatic ring through strong solvation effects, while methanol allows more of the aromatic selectivity to occur. The next slide lists some of the solute types that can show enhanced retention and selectivity on phenyl phases. Many of these compounds are heterocyclic or have aromatic rings that are in close combination with polar atoms. As shown in this next slide, HPLC phases with built-in polarity or polarizability can show more retention and selectivity than C18 when molecules have a polar functional group, such as nitro, hydroxyl, amino, and others. Note that this is the case for simple nitroaromatics. The extra retention for ascentis phenyl is believed to be due to formation of strong pi-pi complexes between solute and stationary phase. Nitroaromatics are pi acids, while the phenyl phase is pi basic, which can help explain the stronger interaction. This next slide shows that ascentis phenyl is significantly better than C18 in retention and selectivity for nitro-containing pharmaceuticals. In the next slide, enhanced retention of aromatic compounds, especially those containing heteroatoms in and near the aromatic ring, is shown for ascentis phenyl compared with ascentis C18, ascentis RP amide, and another phenyl phase that has about equal amounts of alkyl and aromatic character. We can draw several conclusions from this data. Since ascentis C18 and RP-amide behave so similarly, it is clear that the amide group does not interact much with either molecule, and interaction seems to be mainly between the alkyl chains and the drugs. The ascentis phenyl phase attracts and retains buspirone more than trazodone, which must be a result of strong pi-type interactions which are not possible on either C18 or RP-amide phases. It is interesting to note that the phenyl and alkyl selectivity tend to cancel each other out on the phenyl-hexyl phase in this particular case. This next slide shows the structure of some important pharmaceuticals that show extra retention and selectivity on phenyl columns. Note the presence of heterocyclic ring systems. This slide shows that ascentis phenyl is clearly more retentive and selective for these structures. Note the use of methanol in the mobile phase. This slide shows another type of compound that is more retained on phenyl columns. While ascentis phenyl is not significantly more selective than C18, it is more retentive. Note that other phenyl columns either show poor peak shape, probably due to increased silanol activity, or insufficient retention, which can be a characteristic of phases that are prepared on hybrid silicas. The next slide shows ascentis silica used in the aqueous normal phase mode. It can be abbreviated ANP or helic. In this mode, water is strong and organic is weak. Both pH and ionic strength are important variables that must be controlled. ANP or helic works well for very polar compounds and is highly compatible with LCMS. Please refer to other Sapelco seminars for more details on this ANP topic. The ascentis high-performance column line is designed to be successful for a broad range of molecules. All ascentis RP phases show comparable retention for easy comparison and fast method development. They are also highly stable and compatible with all HPLC detectors. Ascentis C8 can be a good alternative to C18 when slightly different selectivity or slightly sharper peaks are needed. Many users prefer to begin method development with an ascentis C8 column. Polar RP columns, such as phenyl and RP-amide, are very complementary to C18 and C8 in that they show different selectivity for polar molecules. When all four popular RP phases prove to be inadequate, a different HPLC mode can be explored. For more information on ascentis and other HPLC products, contact Sapelco Technical Service for assistance.